A ball is thrown vertically upwards with a velocity of 49 meters per second. Calculate the maximum height to which it rises and the total time it takes to return to the surface of the earth. So here we have an object that is thrown vertically upwards with a velocity of 49 meters per second. So the initial velocity u is 49 meters per second. The final velocity is 0 meter per second, and the acceleration due to gravity here will be minus 9.8 meter per second square. There's retardation going on. So we need to find the height or the distance traveled. So the given velocity is the initial velocity 29 meters per second. The final velocity is 0 meter per second. So we use the formula v square equal to u square minus 2as, or instead of a and s you can write gh. And you put your values. Your v is 0, this is 49 square minus 2, 9.8h. And here is the calculation. So you got h equal to 49 square 2 into 9.8, which comes as 122.5 meters. So the maximum height reached is 122.5 meters. Now next we need to find the time taken. For the time taken we can use a formula v equal to u, that is plus 80. We know v is 0, u is 49, your a was minus 9.8, and the time you need to find. So here you put your plus. So on working this out, you'll get your time as 5 seconds. And here they've said find the time it takes to return. So it would take 5 seconds to go up and 5 seconds to come down. So the total time would be 10 seconds. Time of ascent equal to time of descent. What is the magnitude of gravitational force between the earth and a 1 kg object on it? Mass of the earth is given, radius of the earth also is given. So here we have the earth with its mass, say m, and we have another object with its mass. This is mass of the earth, this is mass of the object, and we need to find the force. So formula F equal to g, mass of earth, mass of object, over r square. Now all the values are given here. This is the gravitational constant g. Here is the mass of the earth. This is the mass of the object. Here is the radius of the earth square. In the next step, here you have minus 11 and plus 24. So we put it together here, minus 11 plus 24. This is 6 into 2 becomes 12. Here again, this is minus 12 plus 24. And the plus 12 goes on the other side and becomes minus 12. And this is a calculation. So it will be 9.770 newtons. We'll now learn to derive an expression for g. And we know g is acceleration due to gravity. So here we have the earth with mass, say capital M, and we have an object with mass small m, and there is a force that acts between these two objects. Now this force, say F, is given by gravitational universal law of gravitation, so which is equal to now g, mass of the earth, mass of the object, over the radius of the earth. So because here is the distance r, so over the radius of the earth. Now the same force is also given by another law. There is also a force now acting between these two, and this is given by Newton's second law. And Newton's second law says this force equal to mass into acceleration. But in this case, we are going to take the acceleration as acceleration due to gravity. Now these forces are same, so we equate them. We have F equal to F, which means we have this force between the two objects, which is equal to mg. The m and m cancel, and what we are left with is gm over r square equal to acceleration due to gravity. Thus we see the acceleration due to gravity depends on three. It depends on the gravitational constant, which is of course constant. It depends m, which is the mass of the earth or any planet that you are calculating the g, or of a planet. And it depends on r, that is the radius of the earth or of the planet. It, however, does not depend on the mass of the body. Now in this question, we need to define the acceleration due to gravity and derive an expression for the acceleration due to gravity in the term of mass of the earth and the universal gravitational constant. So acceleration due to gravity is acceleration produced in the body falling under the force of gravity is called acceleration due to gravity and is expressed in the unit meter second minus 2. Now to find the acceleration due to gravity, we know first the force is given by gmm over r square. But by Newton's this expression is given by the universal law of gravitation. But by Newton's second law, we have F equal to ma. But in this case, we write for A, we write G. So F equal to mg. And now we equate both this. This is the force, gravitational force here by universal law, and this is by Newton's second law. And when after we equate, we get our G equal to, so we get m over r square, this is G equal to mg. We cut off this and we get G equal to gm over r square. It is independent of the mass of the object. It's a very important point. A car falls off a ledge and drops to the ground in 0.5 seconds. G is taken as 10 meter per second square, and we need to calculate the other parts. So here we have an object that is dropping. Now when the object drops, the u equal to 0, the initial velocity equal to 0, the g is plus 10 meter per second square, because here it is acceleration, it moves faster down. So we need to calculate the v. This is our question. So we can use a formula for this. Now the time is given as 0.5 seconds. Now time is 0.5 seconds, which is half a second. So we start with v equal to u plus at, and u is 0, your a is 10, and your t is 1 by 2. So when we calculate this, we get v equal to 5 meter per second. So here is what we've got, v, the final velocity. In the next step, we need to find the average speed. Now we know average speed equal to initial plus final divided by 2. So initial is 0, final is 5 divided by 2, which is 2.5 meter per second. And in the end, we have to find how high is the ledge, so the distance traveled. For that, we will use a formula S equal to ut plus half at square. U was 0, t was half second, half a was 10, t square half second the whole square. And on calculating, here is the calculation. You can also take time as 0.5 is the same as 1 by 2. And that's what they have done here. They've taken time as 0.5. And on calculating, we had 1.25 meters. Derive an expression for the force of attraction between two bodies and then define gravitational constant. So first we go to Newton's law of gravitation, which says every body in the universe attracts every other body with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So here are two objects, one with mass m1, another with mass capital M and small m, and they are kept at a distance d from each other. So it was given to us that the force is proportional to the product of the masses. So here we have F is proportional to m1, m2, and it is also inversely proportional to the square of the distance between them. So F is directly inversely proportional to the square of the distance. It comes down, the d comes down. So this is what is written here. So when you put both of these together, you get F proportional to m1, m2 over d square. So here, and the proportional sign, when you change, it becomes a constant. And in this case, the constant is g, so m1, m2 over d square. So here's the expression, k is a constant, which is then changed to g. Now how do we define g? To define g, we know F equal to g, m over d square. Now if mass is 1 kg, if both the objects are of mass 1 kg and the distance is 1 meter, then what would have happened? So we have F equal to g, 1 over 1 square. So F equal to g. So g can be said is equal to the force between two objects, each of mass 1, each of mass 1 kg at a distance of 1 meter. So here we have taken this 1 kg, hence each of mass 1 kg and the distance of 1 meter. And this is exactly what is defined here. G is numerically equal to the force of gravitation which exists between two bodies of unit mass kept at a unit distance from each other.